got research up there, so I do that. Yeah, it's also and lab and legal reasoning. Now I have like notes for this time.
Welcome back. Welcome back. So, the public service announcement a week from today. We'll have our first test. And by the way, just so you know, I was looking back over the when I had the test last time, and the shift was 1 day. So I shift this as this exam is late, but it's late by only one class period. So it's really not that big a deal. So it will be Wednesday, March 5th. Chapters 2 and 3, and frankly, I would consider all the elements in chapters 2 and 3, all the topics. In class, I'm just doing a summary or review of signals and systems. I can't hit every single detail. I give you a flavor and certainly the things that we use. But in studying for the test, I would look at all the material in chapters 2 and 3. Also, we delved into a little bit of section 4. I've been talking about it, calling it section 4.1. It's really through figure 4.1, which is the mixer. So that's really what I mean by that. And so I'll even add that to this. There you go. Okay, so that's really the element in chapter 4 that I'm most, that little block or that little component part of the block is what I'm interested in. It's really the modulation property from chapter 3, but it's covered better in chapter 4 than it is in the table 3.2. So that's why I have it there. And then it's lectures 1 through 9 on Echo Center. Okay, lectures 1 through 9. Closed notes, closed book, no calculator. I will give you Appendix E of math facts.
Like trig identities.
Pardon?
Like trig identities.
There'll be trig identities. There'll be some integrals, some other stuff. So just I don't even know if you'll need it or not. I imagine that sometime over the course of the semester you will want it, but I don't know when that's going to happen. I don't plan the test around it. I just feel like it's a little bit of the extra stuff that you would ordinarily put on a cheat sheet, but not but it's just more uniform.
Just a quick question, whenever you write your exams, do you just think of relevant things and jot it down before? Do you create new ones every year? Do you have basic ideas of what you do?
So yeah, no, that's a good question. You can look over the topics for the first 9 lectures, and if you think about it, maybe there's 2 topics per lecture, right? But maybe at a higher level, there's only 3 or 4 topics that we covered, and so I generally try to sample across those topics. Fourier, convolutions, the interaction of signals and systems, the properties of signals, things of that nature. And so I try to give a flavor for in my questions. I try to give a flavor for that. On how to and again, the homework problem. One of the test questions is going to be a homework problem. There'll be 2 others that will come from me, which means mostly the notes, and that's how I'm all over the map on my questions. I try to structure them so that there's a part A that's easier than a part B, that's easier than a part C, that's easier than part D. That doesn't always happen, but I try to structure it that way. And I do try to put in things that are, especially on the parts, the latter parts. I do try to put in things that you really have to think about. And I won't promise that there's a neat, clean answer for everything on the test. In other words, you should be able to talk intelligently about everything on the test and make a stab at it, but there may not be a clear optimum. I may have a question of fill in the box, put a design into this box, design a realization for something. And that's a design problem. It's open-ended, and so there is no clean 100% answer that is optimal. There may be a number of right answers. There may be a number of answers that get you close and good enough. And the perfect answer may be unrealizable because the device doesn't exist or some other element doesn't happen. Okay? In other words, Not because I'm sloppy or diabolical, but because it's the nature of our field. Okay? Not that you rule out that I'm sloppy and diabolical, but you know, but you know, at least I have it's not intentional, at least. We're going to. There's a few things that I want to go through in a little bit more detail today. Last time we talked about AM, envelope and otherwise DSB. I want to go through that again, and what's really important, I want to include. I want to include what happens when things don't go perfectly right. Okay. One of the elements that one of the skills that I really want to teach you is the ability to work with these signal flow diagrams, to be able to walk a signal through a large number of blocks, you know, and get from the message signal and through the transmitter, through the channel, into the receiver, and out of the back of the receiver. And so I'm going to illustrate that again. I'm going to do that, and I'm also going to do it with when things don't quite go wrong. Okay. A good engineer is really paranoid. So we say, I've got the answer. Now we have to say, what are all the things that can go wrong with the system? Last time we did a lecture on QAM, quadrature amplitude modulation. That was a way of doubling the capacity, term of art, capacity, how much information you get down your channel. Now I want to go over that because I think we went through it pretty fast. And it was a complicated system. And then I want to do the same with some impairments as well. Okay, just so we kind of see that. All right. So let's start with this particular system, which at first glance should be cake. Okay, we've seen that a million times. That's the simplest modulation that we can come up with. So I'll label this transmitter. I have a channel. And later on, in fact, probably next lecture, in the next couple of lectures, we're going to start looking at what happens to this channel where things can start to go wrong with the channel. But for now, Lottie and myself are going to say it's a perfect channel. And what we mean by that is whatever goes into this box comes out of this box. It just multiplies by 1. If this were an AM radio, if we were broadcasting out, this factor would be greatly attenuated. By greatly, it might be 5 orders of magnitude. 5 orders of magnitude reduction. But we could just call it a 1. So this is kind of a back-to-back test. Okay? I'm going to call this intermediate signal X of t. I'm going to call what comes out of the channel Y of t. Here's another mixer at the other end. That's a coherent demodulation. So there's a receiver. I'll call Z of t what comes out of that element. And then you know the answer. So I'm going to put a low-pass filter in. And then what comes out of here, we want it to be M of t. We don't know if it's actually going to be M of t, so I'm going to just put a little prime on there so there's something to mark that that's not necessarily M of t. And what we're going to try to do is we're going to say, okay, if I send out M of t, what will come out will be M prime of t. How close is M prime of t equal to M of t? And in a perfect world, it'll be 1 for 1. In a perfect world, it'll be exactly equal to it. Okay? If I just leave this alone, in the perfect case, if I put this as a perfect case, does anyone remember the relationship between M prime of t and M of t? 1/2. Right? That's very, very good memory. And so we've done that problem before. We know that when we get through the low-pass filter, when we do the 2 modulators, we have to reject half of our energy, but at twice omega. And so we're left with exactly half the power. So in the perfect case, m prime of t is equal to 1/2 of m of t, and I've suffered some small degradation of my signal by going through this. Okay? It's not a big deal, but it's there. Okay? And so that's the perfect case. Okay? What I want to do today is I want to talk about imperfect cases. And what I mean by the word I like to use is impairments. Generally, anything that can go wrong with my channel, anything that can go wrong with my system, my communication system, will be some sort of impairment. The bigger the impairment, the worse this relationship is going to be between m prime and m. Okay? We'll see. Things can get markedly bad. What happens if there's a block in there what happens if this channel is equal to 0? In other words, I have a fiber optic cable and a backhoe is digging to a nice trench and doesn't know my cable is there and rips it out. I would model that situation as the channel equal to 0, and what would be m prime of t? 0. And so 0 would be markedly different from m of t, right? It's a case that really happens. It's ludicrous to model, but it illustrates what I'm trying to get at. Okay? Now, imperfections. I don't want to mess with the channel today. Oh, okay. Let me back up even a little bit further. The reason I have x of t in there, y of t in there, and z of t in there is one of the goals of this course is to be able to walk a signal down a system like this. Okay? And so one of the skills that we're getting and we're developing, and I've done it by inference now, and today I want to be explicit about it, is we should be able to figure out what x of t is and also x of omega. We should be able to figure out y of t and also y of omega. We should be able to figure out z of t and also z of omega. We should be able to figure out m prime of t and also m prime of omega if we need it. Okay? And so just to review, x of t would equal x of t would be the product of m of t and cosine, the mix of m of t and cosine omega ct. So this would be equal to m of t multiplied by cosine of omega ct. The channel is equal to 1, so y of t is just equal to 1 times m of t cosine of omega ct. Z of t here will equal y of t times cosine of omega ct. And if I go even further, z of t will equal 1, which I'll leave off, m of t cosine of omega ct cosine of omega ct. Okay? If I want to simplify some math, m of t cosine squared of omega ct. Okay? So that's the art of walking my signal through the system. In that context, I give you the system, I give you an input, I give you some other information, and you walk yourself down the system. In other instances, I may give you some mathematics, and you may have to come up with the block diagram or the system. And we did an example of that last time with the envelope. We knew what the mathematics of it was, and then we talked our way through what the signal flow diagram was going to be. Okay? Well, let's now do some imperfections. I have m of t. I have my local carrier. I have my channel. And I start thinking about what can go wrong. And I'm not willing to bet, I'm not willing to make some problems with the channel yet. I will next time or the time after. This stuff is under the transmitter control. So we'll call that what it is. But when I go to write this term here, I start to see a lot of problems that can come up. Okay? I can start to see a lot of problems that can come up. For example, I can install a local oscillator that doesn't have the right frequency. I can install a local oscillator that doesn't have a right frequency. And by the way, if you decide that your carrier is going to be 101,000 hertz, 101 kilohertz, for example, and you go out and you specify a transmitter, an oscillator for that, the company's going to ask you for an error associated with that. And you can't just get away with saying 101,000, because there's always going to be some issue of match. And if you specify it to 6 significant digits, that's going to be more expensive than specifying it to 3 significant digits. If you specify it to 9 significant digits, that's even more expensive. And so part of your job as an engineer is to specify it with the least precision that you need. Well, specify with the precision that you need, not the precision that you think you need. And that means that you have to look at these error analysis. So you can look at this as saying, okay, omega c, I'll write it a slightly different way. Cosine of omega c, so I'll say it's going to be the same frequency plus some small shift in frequency that's going to be my specification or my error times t. Okay? So both of these forms take pretty much the same, they're modeling the same thing, which is that my cosine is going to be, my cosine at the receiving end is not going to be exactly equal to in frequency to my cosine at the beginning end. And that can happen because it's a hot and sunny day and this guy is varying all over in frequency. It can happen because I want to specify a part and I need to specify a tolerance on that part. Okay? So it's just, so for whatever reason, that's one type of impairment. Okay? We also got a hint last time when we looked a little bit at QAM that the phase of this guy matters, right? The phase of this guy also matters. So there could also be another problem where I have the right frequency, but I have some small phase shift associated with that. Okay? Now, in either of these cases, I'm going to figure out that my system is going to be about the same. Maybe I can learn how to tweak this box or add something else in afterwards to fix it. But the first step is my system as designed, looking at the tolerances or looking at the imperfections. Okay, impairments. And now we see that now we fully recognize that this prime, given these imperfections, is going to be even worse than just a simple factor of 2. Right? So, mismatched oscillator. Okay. So, I think I labeled this guy Z of t. Is that right? So Z of t will equal m of t multiplied by cosine omega ct. That's this signal right here, multiplied by 1, mixed with my new signal. And I'll start with that case. Okay. It's just the idea is that you figure you get the sense of how to do this. But the results today are interesting in and of themselves, but what's much, much more important is that you develop your paranoia. You're able to look at a perfect design and anticipate impairments, problems, and go ahead and analyze for those issues. That's part of the engineering task. Okay? Think about what you're doing upstairs in lab. Right? It's that there's a perfect idea in the lab papers. Once you put it in your circuit, you don't have the right you don't have the right capacitors, resistors, and so on. You've got to look at the result of all that. Okay. All right. Trig identity, huge here. This is the guy that we operate on. There we go. Do you agree with me on the trig identity?
Yes.
Okay. Quick test. If del of omega equals 0, then cosine of 0 is equal to 1. Sine of this guy here is equal to 0, which means this guy goes to 0. And I'm left back with the del cosine of omega ct as if nothing else happened. So if del omega was 0 and I have perfectly matched oscillators, then I've returned back to my perfect case. Okay? So just some math. Z of t looks like this. Trig identity.
See the sine of 2 omega c t divided by 2?
Like that.
The second one, can you turn that into 1/2 sine of 2 omega ct?
The second one. This guy here?
Yes, sir. Times.
Cosine sine. That one, yeah, actually.
Okay. So what I get is I get that. Okay. And this omega ct is going to equal this guy here. So this will also always equal 0. Right? I don't know if that's what you were saying, but I think that's right. So this guy is 0, and then I just have the sine of twice omega ct. Is that what? Okay. Good. So now we low-pass filter this. And this guy goes away on the low-pass filtering side. This term also goes away for low-pass filtering. So I have m prime of t, which is equal to 1/2 m of t times cosine of del omega t. Okay? If del of omega is equal to 0, if del omega is equal to 0, the cosine of 0 is equal to 1, and I reduce back down to my perfect case. But the whole point of doing this was to say, what is my tolerable level of del of omega? What is my tolerable level of del of omega? So this is a bit challenging. How do I interpret that cosine of del omega t?
We want it to be somewhere close to 0.
We want it to be close to 0. So what if it's 1 part in a million? So well, let's find out. Let's think about it. Let's say it's 1 in 10 to the 5th, 100 kilohertz omega c, more or less. 1 part in 10 to the 5th. That's way out. Pennies on $100. 1 penny on $100 or something like $1,000. Should not care about that. But that would be 1 hertz, right? 1 hertz separation between those two receivers. So this is actually a cosine of 1 hertz times t. Every second, this m of t is going to be blanked out. At least that's what I read. That's the way I see it. Do you see it the same way? This del of omega is a variation in frequency. It's the beat frequency. It's going to go up and down. Up and down. So this signal m of t is going to get softer and louder and softer, louder. And the frequency at which it gets softer, louder, softer, louder. That's annoying, isn't it? But I'm modulating my voice at about a hertz to be loud and soft, loud and soft. And here's the whole lecture trying to be. That's really distorted, right? That's 1 part in 10 to the 5th. And it brings you right into baseband. And so that gives you the tolerance. So that's a very, very severe penalty. That's a very, very severe impairment if I'm allowing these two local oscillators to run without talking to each other at all. Okay? So how can I fix this? Shall I go to an even smaller frequency? So 1 part in a gazillion? Okay, so if I go 1 part in 10 to the 9th, then this now becomes 0.001 hertz, which means that fade in and fade out occurs on the order of 10-15 minutes.
But once it fades out, it'll take 10 minutes to come back.
Mm-hmm.
Would
But at least I get to listen to a song if I time it right.
you increase it to approximately pi or even 2 pi?
This is a raw frequency. So this is a frequency. I don't measure frequency in terms of pi. I measure frequencies in terms of hertz or radians per second. So the answer is this is pretty intolerable. And so what I have to do is somehow I have to get the information from this guy into here. So if you remember the envelope, I broadcasted the carrier. Remember when I broadcast the envelope, I broadcasted the carrier. And so if I broadcast the carrier, then I can use the carrier to lock a fancy circuit. I've got to figure out exactly how to do that. But if I use that information to lock this guy at the right frequency and even at the right phase, then I can get rid of this impairment. Okay? So this is an interesting, I love this example, right? Because our intuition is, oh, we'll just make it really small. 1 in a million should be fine. But it's not. Okay?
So I have a question.
Yeah.
If your message is varying and you have some sort of tolerance on, I guess, between the transmitter and the receiver, if you're transmitting your carrier as well, isn't there also a tolerance for that? Or is it much easier to manage comparatively?
Right. So it depends on the hardware that you use to lock that signal. First of all, you have to have enough power to detect it. Second of all, if it's so far out of whack that it may, the details of the, let's say you're using something called a phase lock loop, which we will talk about, but not for another month or so, not for another 3 weeks or so. That phase lock loop will restore the frequency to omega C if it's close, if it's within the bandpass filter of the loop. Okay, so you can imagine there's some sensing on that carrier, and if it's just so far out, you're not gonna know it. You might lock onto the adjacent radio station, right? You might lock onto the adjacent radio station if you're really bad. Okay. So, anyways, that's just a little bit of that impairment is actually quite serious. That particular impairment is actually quite serious, and it requires a drastic change in how we might approach the solution to that problem. Okay. What I'd like you to do is I'd like you to do this case. Okay? And it's really the exact same case. It's really the exact same case with omega C equal to omega C plus del omega.
By delta, do we just mean like a very small, like?
Yes, yes, good point. This is pretty standard notation, so that I'm saying this omega C is a big number, and this is a small. I'll use the term perturbation. Perturbation. Small kick. Okay? A small change of it. A small perturbation on it. Or I can say it's an error term. It's the error term. Or I can say it's the tolerance. Okay? In fact, let me write that down. Tolerance, error, perturbation. Depending on why you're actually analyzing that. When you do a lab, you usually do an error analysis, right? So if you put in a resistor, if you design for a resistor of 100 ohms, and you have a 5% tolerance, that means you've got to run your circuit with 95 ohms to up to 105 ohms, and that's the range. You see how your circuit behaves across that. And it's very similar analysis. I get the sense a lot of you don't do that. Okay. if I'm ever have a lab again, that'll change.
Delta, or you put down an omega and then those terms.
So we want to talk about mismatched oscillators. Okay. Actually, this is fine. This is a good segue into what I want to do. Mismatched oscillators. So we're talking about frequency variations. Both of these are frequency variations. Okay. Now, how do I write mathematically a frequency variation? Well, I can just say that this frequency is not equal to that frequency, or I can say this frequency is equal to this frequency plus some perturbation or plus some tolerance or plus some error. But if I set omega C prime equal to omega C plus del omega, it's the same thing. Okay? Whether or not you're talking about, if this is 101 kilohertz, then is this 101 kilohertz and 1 hertz? or is this 101 kilohertz plus 1 hertz? Okay? So it's just your, you know, your preference. And so now let's do the phase. Now let's do the phase difference. And I'm motivating this by looking at the QAM from last time and knowing that the system, this coherent detection system, knows the difference between a cosine and a sine. So for a phase difference, I have my new z of t. That signal is the signal that goes into my low-pass filter. So it's right after the modulator. So if the local oscillator is the right frequency, but it's shifted by phase by some number of radians in phase, then I have a z of t is equal to that. And again, if I use my trig identities, cosine A cosine B is equal to cosine A minus B plus cosine A plus B. So trig identities from there to there. This is one of the reasons why you like Appendix E on exams. So you can just see what these trig identities do without losing track of the flow of what you're solving for. These guys go to 0. These guys go to twice omega CT. So I have m prime of t. If I do my low-pass filtering, I lose that term altogether. So this is equal to 1/2 m of t times the cosine of theta. Okay? Talk to me about what that does for me.
Completely eliminates it or somewhere in between.
Okay? This cosine will vary between -1 and 1. Okay? So it will either give me the entire signal, 1/2 m of t, or it'll give me 0, or it'll give me somewhere in between. Okay? If theta is small, if it's a small angle, then this will be 1 minus theta. Actually, theta is set over 2, I believe, right? So look at this as a quadratic. And I start high and I go down. So if I have a small error, then I just have some smaller signal. Instead of 1/2, I have, you know, 1/3. You know, instead of 0.5, I might have 0.45 of my signal. Not that big a deal. So this is just an attenuation, and for small thetas, I have just a smaller signal out. I have to crank up the gain a little bit, or put my ear closer to the speaker. Of course, if that's 90 degrees, then that goes all the way to a sine, and that goes to 0, right? So if I go all the way out to 90 degrees, then my cosine of 90 is 0, and I've lost my signal altogether. Okay. What else could happen?
Have a really large data.
Yeah, but remember, it's all cyclical. So if it's 2 pi or 2 pi and a little bit, you're right back in the same center. So that phase information just wraps again and again and again. It's a periodic function.
Could you get like, the opposite of your signal?
I could get a negative signal, but probably that's not a big deal. Probably I'm rectifying it anyway, and I'll just that's probably correctable. Because the envelope appears on the top and the bottom of it, and if I'm shifted just by a little bit, I don't think that's going to matter too much. But think about this. Under what condition are you going to get a constant phase shift? Well, are you going to get a constant phase shift? That's the question. I'm modeling the output as having a constant phase shift. Is that a realistic case? If I'm sloppy enough to have a phase shift, I'm probably sloppy enough not to fix it into place. Which means that's going to slide all over the place, which means I'm probably going to have theta of t. And then I'm back exactly to where I was before. That this is now time varying. This cosine is now a time varying signal, and it's going to breathe in and out. A constant amplification isn't going to cut it. Sometimes I'll be at 0.5, sometimes I'll be at 0.5, sometimes I'll be at 0.42, sometimes I'll be at 0.48. So these guys are going to slide all over the place, and then I just don't know how much that wanders. Okay? I said these were impairments. I said that these are when things go wrong. Right? That's the reason to do this. Good engineers are paranoid. Good engineers look at a system and they say, what can go wrong? Okay? Now, with that in mind, I want to go back to the QAM case. Okay? And the transmitter of the QAM case was built so that I could use the same channel to accommodate a message 2 and a message 1. Okay? And so what goes into my channel is a signal psi sub QAM of t that goes into my channel, and it has the information for both of these guys on it. Now these are modulated, and they're modulated at the same carrier frequency. Modulated at the same carrier frequency. Except that I'm modulating one with a cosine omega ct, and after I phase shift that local oscillator, I'm modulating the other one with a sine of omega ct. And so this is my transmitter. Transmitter, channel, and we'll look at the receiver in a second. So that signal, psi QAM, is going to be M1 of t, that's this guy here, multiplied by the cosine, goes into the summer, this combiner, so I have a plus there. And then this term that's coming up through here is going to be M2 of t sine of omega ct. So now on my receiving end, I'm going to use a coherent detection. Especially motivated to do that because I have the phase between this guy here and this guy here is what makes this thing work. So I have to keep track of that.
Quick question. So coherent detection keeps track of the phases.
So coherent detection is when I use a local oscillator. So we've looked at two detectors for AM, right? We've looked at the coherent case, which uses a mixer and a local oscillator. And we've also used the diode as a rectifier, okay, to just pull out the envelope. And with a little bit of thought, you can recognize that the diode isn't going to work with this because I've got two frequencies, two sinusoids here. They're all just going to get rectified and muddled together. So the heterodyne system is what we really want. The local oscillator, the coherent case. All those are terms of art. And I'm using them purposefully so that you know that they're all related when you hear them in conversation, or when you use them in conversation. Okay? So I know in my receiver I'll have mixers. I've done this problem before, so I know I'm going to have low-pass filters after the mixers. I need to have a local oscillator in there. Oops, I have that arrow the wrong way. That's not good. So I'll feed the cosine into that mixer, and I'll feed the sine into that mixer.
Would it matter if you add or subtract pi half because you're just going back to the MT?
Pardon?
From your sine, and you go through channel 1, and you're trying to get back M2, and you're using pi half, does it matter which?
Whether this minus sign or that minus sign?
Yeah, does it matter?
Yes, it matters. Just figure it out. Because this is a delay.
Yeah.
So this block is a delay block.
Okay.
And so what I want to do is I want to delay it by 90 degrees to turn a cosine into a sine. And I'm not sure if that's delaying by minus 90 or 90. But you just, I know it's 90 degrees, but you just have to think about it.
So if I go 90 in one way, when I try to retrieve the signal, I have to go 90 back.
I just want to go cosine to sine.
Okay.
That's the reason for that phase block. Okay? So what we're going to do is we're going to look at impairments. And we're going to say we're going to do exactly the same thing we did before. What happens if that cosine is different? Okay? What happens if that's not a perfect cosine? I'm going to call this x1 of t, and I'm going to call this x2 of t. And I'll put a little, and then I'll call this m1 prime of t, and this m2 prime of t. And I'll put a little dash on there just to say that it's not perfect. So as soon as I have that in there, it's not perfect anymore. Okay? I don't want to go through the. I don't think we need to go through the perfect case again. It'll be obvious when we do the math on this. Okay. So, what we need to do and I'm going to do the phase part first. So supposing this guy here is off by a phase shift. Okay? Then so if my local oscillator at my receiver is a cosine but is shifted over in phase, then what will happen is that there'll be a cosine shifted over in phase here and a sinusoid shifted over in phase there. And a sine shifted over in phase there. So my x prime of t, my x1 prime of t, that's the output of this mixer. That's the output of this mixer, is going to have the QAM signal multiplied by cosine. Now it's shifted over by by some number of radians. And to be clear, my psi QAM is m1 of t cosine omega ct plus m2 of t sine of omega ct. And I do my math. Now, ordinarily, in a perfect world, if that theta was going to be gone, then this guy would have the DC term and the twice omega frequency term, and that would average out to m1 of t. That's what we'd like. Yeah, and this guy here would be orthogonal. The sine and the cosine would be orthogonal. So when I average that, or low-pass filter that guy would go away. Or if I use my trig substitutions, I'll have omega ct minus omega ct and omega ct plus omega ct, and the sine will go to 0, and that whole term will be rejected. Okay? But that's not what we have. This cosine here now has a little bit of sine and a little bit of cosine in there. Because I've shifted over this cosine, it has a little bit of a sine and a little bit of a cosine. And so there's a little bit of a cosine here, a reduced cosine here, and a little bit of a sine here to let this guy through. And that's a problem. So, continue with the math. Actually, each of these terms has two terms, so there's 4 terms that I have to keep track of. Okay, so I have 4 terms. Cosine A cosine B is cosine of A minus B plus cosine of A plus B. Sine of A sine of B is equal to sine of A minus B sine of A plus B. Trig Identity. Here's my cosine minus cosine A minus cosine B, cosine A plus cosine B, sine A minus B, sine of A plus B. Okay? Everyone okay with that? No? So if I low-pass filter, that high-frequency term goes away. That's twice omega c. Low-pass filter, this guy goes away. My omega c's are exactly the same, so this guy is 0. And this guy is 0. And so now this is equal to, oh, I know why you're all puzzled.
Yeah, go ahead and like put a 2 for the...
Yeah, we could. I left that off this time. I left it off this time. Yeah, absolutely. You can follow Lati. And I did that way last time. This time I didn't. So I'm just working my way through the math. And I forgot my trig identities.
Maybe negative
Yeah.
cos m1t cosine negative theta.
I'm sorry, say that again. Which one should be negative?
M1.
Both the thetas.
Both thetas are negative, but the
Cosines. Oh yeah. So yeah, that minus sign. That minus sign becomes a plus. And you see what I did here? I put a minus sign there. Okay. Yeah. Cosines are even, and sines are odd. In fact, that's actually how I remember this trig identity on the rare occasions that I do remember it. So now you see what's going on here. Okay, a little bit of a phase shift here. The phase shift causes 2 problems for the QAM system. Here's my reduction in signal. This is what we saw before, right? This is my reduction in signal. Cosine of some phase shift is not going to be 1. It's going to be 1 minus some number. So this number, instead of 0.5 m1, this is going to be like 0.45 m1. Okay? And so this is my decreased amplitude of the signal that I wanted. Okay? That's not that big a deal. Okay? As I tune out of this guy here, though, more sine increases. Excuse me. I have more sinusoid there. So the sine of, if theta were 0, that would be my perfect system. This guy would be 0, but it's not. This is actually, for small thetas, that's approximately equal to theta. And so this guy now lets in some of M2, and so we call that crosstalk. So now you're listening on the M1 channel, and if I don't control my phase very well, then what I have is I have crosstalk in there. Now think about it. If the theta of t is varying, that's not too different from saying that my frequency is shifting. The math will work out about the same. In fact, I'll encourage you to go ahead and do that tonight. Is to do the impairment where I have an omega prime going on. So what will happen is the amount of as this wiggles around, this signal will go down, and the amount of crosstalk will now come up. So instead of talking and going smaller, softer, and then louder, and then softer, and then louder, what we'll have is somebody else speaking louder than softer, louder than softer. So you're switching back and forth between the two channels. So if this theta C is changing, as it would be for a time system, then I'm hearing M1, and then M2, and then M1, and then M2, and then M1, and then M2. Okay? So these are some of the impairments that can come out. So the answer, so what this tells you is you have to engineer that local oscillator on the other side so that it's at the right frequency and it's at the right phase. Otherwise there are going to be some problems. Okay?
This is all assuming that the phase is changed across time. It's not fixed, right? It's not a fixed phase shift.
Well, if this is a fixed phase shift, this is exactly literal.
Right.
And so forever, I will hear 90% of this guy and 10% of channel 2. Remember, you might have heard the term party line. If you were sold a party line, that means that you would sometimes hear a crosstalk in two channels, two phone systems sharing the same channel. You would in fact hear some of your neighbors' conversations. Maybe that's happened to you even recently.
It's not like when you're in between two radio stations. My science
So two radio stations that would be broadcasting at the same carrier frequency, and you're driving out in the middle of the country, and you're leaving Houston and you're going to Dallas, and you're catching something half the time you're in that transition zone. It's a little different. That's a little different situation. There you're just subject to channel losses. So channel losses are varying, and sometimes your ionosphere is kicking a signal into you, and then it's not because you're driving and moving. So I think this is really just both are you're trying to listen to this, and it's like having another conversation there. So we can mimic this, right? If I lecture and then somebody has a conversation, you'll hear me and you'll hear them. You'll hear me 90%, but you'll also be a little distracted in trying to listen to that. The cocktail party problem.
Was this the reason why back in the old days when all the phones were just wired, that people would sometimes you would hear another conversation?
Well, so there's a crosstalk is the hearing of somebody else's conversation on your line. And it will come up in a variety of different ways. There are different impairments that will cause crosstalk. This is one such impairment that will cause crosstalk in a QAM system. Okay? So, now, let's just go back here and think about what we've done today. I'll stick with the QAM system because there's a little bit of fun here to be had still. We reviewed this whole system. The QAM is a very important capacity doubling scheme, and so the review of that is absolutely important. The second thing we did was we didn't just say we're going to keep everything perfect. We thought paranoid, like an engineer, and we figured out, okay, what happens if this guy isn't perfect? And so the particular imperfection that I talked about was if this guy was cosine of omega CT plus some phase shift. Okay? We analyzed it for both a static phase shift and also a wiggling or time varying phase shift. But you could also say, well, what happens if this is a different frequency? Okay? And then the mathematics would look a lot more like what we did earlier today. Okay? And it's very, very nice to talk about crosstalk, and it's very nice to talk about this fading and all these kinds of impairments. That's all part of the lecture. But what's far more important is the fact that you are able to come up with your own impairments, your own what-ifs, your own problems in your system that you're working with, you're designing, and that you can come back to these block diagrams, these signal flow diagrams, and analyze the perfect case versus the imperfect case. Okay? So try not only to take a look at the examples that we're doing, but also learn from them so that you can apply them to other situations. Okay? And now I hate to phrase it this way, but I don't have much choice. This is one of the ways that I make test questions. is if I do the perfect case in class, then I might go into and I'll go in and I'll say, well, in class we did the perfect case. For the test question, what happens if the oscillators are mismatched? Or what happens if there's a phase shift? Or what happens if the cosine has 2 terms to it? Or what happens if the channel has some funny stuff on it? Okay? So that's where interesting engineering problems and also interesting test problems come up from, is the cases that not just what we do in class, but variations on what we do in class. Okay? And you should already be doing that. You should already be thinking paranoid. I know that my resistor should be 100 ohms, but I also know that I have a tolerance. I'm using 5% resistors. And so the real resistance is going to be anywhere between 95 and 105. And so I have to make sure that my circuit works if I get a 95 ohm resistor, or it works if I happen to ship a board with a 105 ohm resistor. Right? So think about it. You're doing a design. It depends on that resistance value. You're shipping 100 boards, 5% resistances. Not everything is going to be at 100 ohms. Some are going to be put down to 95, 98. Some are going to be at 102, and some are going to be at 105. And all the boards have to work. Oh, but guess what? On a board, there's going to be maybe 100 resistors, and maybe 50 capacitors, and different transistors. And all of those are going to have tolerances. And so the statistics associated with all of those variations have to be added up. And some boards are just not going to work from unluckiness. And that goes into a whole other issue called yield. Okay? Which sounds like some of you have heard of, maybe even experienced. All right. A couple more minutes left in class, so I'm going to introduce what we'll talk about next time. So, what we got into this QAM business by saying, I'm in a double sideband system. I'm wasting my bandwidth. In a double side in DSP, I'm wasting my bandwidth. My M of omega looks like this. After I mix it, it looks like this. But really, this piece here is just redundant. These pieces here are just redundant. So I should be able to reuse those. QAM gave us one way of doing that. And QAM is actually a very, very preferred way of doing this. But there's another way, and it's called single sideband, or SSB. So it's another way to double your bandwidth of an AM system. Okay? And I don't want to scare you, but I do feel it's important to warn you that what we're going to be doing in our single sideband lectures are going to be some of the more difficult mathematics of the semester. Okay? It's going to be some of the more difficult mathematics of the semester. Conceptually, and also some of the mathematics will be a little bit new and foreign, and some of the proofs themselves will be subtle. Okay. So what we'll do is it'll be challenging. The next few lectures will be challenging when we go through the single sideband stuff. Okay. So I just want to get that out there. So you'll want to pay attention. Now, what I'm going to do to help us along is I'm going to do 2 examples. I'm going to do the single sideband in a communication context, and I'll be working entirely in the frequency domain, where I'll be doing some stuff in the frequency domain. What I'll do is I'll do exactly the same mathematics, but I'll do it in the time domain for a completely different application. And so what I'll do is I'll teach you the material. I'll teach you the mathematics twice, and I'll teach you two different concepts. And the first concept will be a communications one, and the second one will have to do with filtering. Yeah.
And so then on the exam, you'll ask us to do each one of the other one?
Well, I'm going to be in class do both of them.
Okay.
So if I ask you one or the other, you will have seen it in class, provided you showed up or you watched it on Course Echo. Okay, because purposely what I will do is I will cover the material twice, once in the frequency domain and once in the time domain, because I want you to see and appreciate the mathematics of the derivation. And then, by the way, if I do that, then you learn two different applications for the same mathematics. Okay? And one of those applications, the one from filter theory, is one you've actually seen before, and now I just get to give you some rigor behind it. Okay? And you'll see all that as we go along. But to begin with, there's one theorem. If I have g of t and g of omega, and they're Fourier transform pairs. Okay? Now, supposing g of t is not a real function, then g complex conjugate of t Fourier transforms to g of minus omega. Okay? And there's a quick little proof of this. So start with g of t. Take the Fourier transform. That's the definition of the Fourier transform. All I've done is I've written down what the Fourier transform is of g of t. Okay? That gives me g of omega. Well, this is an equality. This is an equality. So if I go through and I say g complex conjugate of omega, that's going to equal, the integral doesn't change, but this g of t will change. That'll be complex conjugated. Oh, and then I have a minus j up here, so that's got to be now e to the plus j omega t dt. So if I know this is true by the definition, and I go through and I complex conjugate the left-hand side, then I complex conjugate the right-hand side. And that means I turn that into a g star, and that means I flip the sign on that j, right? Okay?
So if you want the j to remain negative, we have to use...
Yes. So I want to know what the Fourier transform is. So now if I say g complex conjugate of minus omega, that's still g a star of t. But minus omega means I flip this back, e to the minus j omega t dt. And this is equal to then the Fourier transform of whatever's here, which is g star of t. Okay? So that's our little preliminary theorem that we're going to need for single sideband AM. Okay? And I think we covered, I think that was covered in chapter 3, probably, maybe. But this is a particularly, this one will come up. Okay. So on Monday, it's Wednesday today, right? So on Monday I'll come back and I'll do the first little bit of single sideband. On Wednesday we'll have the test. Midterm grades are due by Saturday, so I'll be grading your tests on Wednesday night, Thursday, and I'll post them Friday, Saturday-ish. You'll be on spring break. Have a great one.